Example 4.4.7. The setup for this one says, you've just won the lottery. Congratulations. The jackpot is advertised as 300 million. Reading the fine print, you find that you have two choices for how to receive the winnings. The prize may be paid out as an annual annuity of $10 million over 29 years, with the first payment today and the 30th payment 29 years from today, or as a single lump sum cash payment of $130 million today. You enjoy your job and do not plan to quit working. You decide that you will invest the winnings to earn interest and only start withdrawing payments when you retire 30 years from today. That is, if you take the lump sum payout, you'll invest it today and earn 8% interest for 30 years. If you take the annual payments, you will invest each payment when you receive it and earn 8% interest on each payment. Which payout option offers you the highest future value? Okay, a couple of notes before we dig into the technical aspect of actually working this problem. One is on how lotteries tend to be described. The jackpot is called a $30 million jackpot, but if you were to choose to just accept one single check today for the full payout, it would only be $130 million. And that's pretty typical with lotteries. Typically, you'll find that the actual payout will be half or even sometimes less of the described jackpot. The other option, the reason they can call it a $300 million jackpot, is because the annuity is 30 payments of $10 million. Of course, it's spread out over 30 years, but it's still 10 times 30 is 300 million, at least nominal dollars, that they're paying out. Now, we know at this point that those have a time value component to them, and so those payments received 30 years from today, if we were to express them in today's dollars, are worth a lot less than $10 million, and we need to account for that because of the interest we could have been earning had we received those cash flows sooner. All right, so that's just a quirk about how lotteries tend to be described. The other thing I want to say about this problem, it also applies to the previous example where we're calculating the present value of the lottery winnings, is that I know it's not very likely that any of us are going to win the lottery and be in a position of making this decision. And let's face it, would you rather have 130 million today or 10 million spread out over 30 years? We'd probably all be pretty darn happy with either option and wouldn't be too upset. But there are scenarios where we will have to make similar decisions because we'll have this cash flow structure to choose between, or we have these cash flow structures to choose between. One example is with retirement savings, especially in defined contribution plans, so pension plans that a lot of government employers still offer, although it's pretty rare in the private sector now. Typically, with those type of plans, when you reach retirement age and are eligible to start withdrawing funds, you'll have the choice of either receiving a lump sum today and deciding how to invest it and spend it yourself, or you could receive a defined benefit, a set number of payments over a defined period, or a set amount of payment over a defined period, and you'll have to decide which one of those is more valuable to you, which one you'd rather take. Another case that's less fun to think about is payouts on life insurance contracts. If a loved one passes away, has a life insurance policy, and you are the beneficiary on that contract, typically you will have a choice between, or often I should say, you'll have a choice between receiving a single lump sum payment immediately or drawing down an annuity over a defined period of time. So likely we're going to have to face one of those scenarios at some point, and so the tools that we'll use to evaluate this lottery example will apply to real life scenarios that we will almost certainly face at some point. It's just a little more fun to think about the lottery than losing a loved one, so we'll think about winning the lottery as we learn how to evaluate these types of cash flows. Okay, now let's actually dig into this guy. So we have two choices that we need to choose between. We can either take a lump sum payment today, or we can spread the payments out over the next 29 or 30 years, just depending on how you define the year, whether you're thinking about the end of year 29 or the beginning of year 30. So we've got a time value money problem. We need to evaluate them. And so we're going to use our three-step process where step one is mapping out the cash flows so that we can then identify them and see which tools we have available to us to solve those cash flows or to deal with that type of cash flow. All right, so we have two options. The first one is the lump sum payout. And with the lump sum payout, we are going to receive $30 million today. I'm sorry, we're going to receive $130 million today. We're going to invest it and earn, we think, 8% on that investment. And then there'll be no other cash flow. So 1 year from today, there's no cash flow there. This is just going to be sitting in our account earning interest. We're not going to draw it down at all. All right, so we'll have no cash flows. Until we get out to the end of year 30, and that is finally where we will allow ourselves to have access to the full amount in our bank accounts. That $130 million gets deposited today. It's going to sit and earn interest for 30 years. So what we want to know is, what is our bank account balance at the end of 30 years that we can then start drawing down and spending as we see fit. All right, so this is just a lump sum payment. We've got one cash flow up front on the timeline, and we want to know what it's going to be worth at the end of the timeline. All right, once we've identified it as a lump sum cash flow, we know that we have 3 tools available to us. If we look at our cheat sheet, we have the different types of the way lump sums might present to us. And here's our 3 tools we could use to evaluate it. We could use the present value, future value, lump sum formula, which need to add this equation 3.1, 3.2, 4.01, and 4.02. These are all just different versions of the same formula. We could use one of these to evaluate it, just depending on what information we've got and what we're looking for. We could use the time value keys and financial calculator, and we'll look at both of those solutions in this example. And the spreadsheet, that answer is in the text, but we're going to skip over it for this video just to focus on the solution tools that tend to be available to us on assessments. All right, so that's easy enough. We also have another option we need to evaluate, though, and that is the annuity payout. All right, and with the annuity payout, our cash flows look a little bit different. With the annuity option, we receive immediately a $10 million payment. We, of course, are going to then turn around and invest that and let it start earning interest at 8%. And then 1 year after that, so at the end of year 1, or we could also think of that as the beginning of year 2, we'll receive the second $10 million payment. 2 years from now, we receive another $10 million payment. And that pattern is going to continue, so we'll say ... out to 29 years from today, we'll receive the 30th and final $10 million payment. But we're not quite ready to draw down on this account balance yet. We're going to let it still earn interest for 1 more year until we get out to the end of year 30. And at that point, after we've collected interest over these 30 years, we'll allow ourselves to start drawing down on it. So the question is, for this problem, which one of these 2 payout options will give us a higher future value? Which one will give us a higher bank account balance as of the end of year 30? All right, so this annuity option, the problem straight out tells us that it's an annuity, so we know we're dealing with some type of annuity, but there are 3 types of annuities it might be. It could be an ordinary annuity, it could be an annuity due, or it could be a growing annuity. Well, we can throw out the third option. We know it's not a growing annuity because the payments are level. It's the same $10 million each year. So we know we're dealing with either an ordinary annuity or an annuity due. And if we take a look at our cheat sheet under annuities, we have the example of an ordinary annuity, which is defined as a finite series of equal cash flows at regular intervals paid at the end of each period. So when we map that out on a timeline, it looks like this. We have no cash flow at time period 0, at least not an annuity cash flow, not one of the payments. And then our first cash flow is at the end of year 1, the second one at the end of year 2, and on until we get the end of the timeline, and our last cash flow is at the end of the last period. Well, this isn't what this particular cash flow looks like. In this example, we actually have the first payment up front. The last payment is at the beginning of year 30, and we're looking for a value 1 year after that. So let's scroll down and look at the annuity due. This guy is defined as a finite series of equal cash flows at regular intervals paid at the beginning of each period. And when we map this type of cash flow out, we can see we've got the first payment at the beginning of year 1, which is right at the 0 tick mark. The second payment is at the beginning of year 2, which we can also think of as the end of year 1. And the final payment is at the beginning of the last year, right, or the end of the previous year. And then we have this blank spot on the end of the timeline where the end of that year has no cash flow associated with it. Well, this is what we're looking at here with the lottery example. We've got an annuity due where the payments are happening at the beginning of the period rather than the end. All right, so which tools are available to us are actually exactly the same as with an ordinary annuity. We've got the present value, future value of an annuity due formula, a time value money keys and a financial calculator, and then of course a spreadsheet, which we'll skip over for the sake of this video. Well, let's see. All right, so we've labeled both of these guys. Or we put them on the timeline, rather. So let's call the lump sum payout, let's call that option 1. And then the annuity payout option, option 2. So option 1 is a lump sum payment. Or let's just say a lump sum cash flow, or CF. All right, option 2 is an annuity due. All right, once we've identified those, in step 3, where we're going to evaluate these guys, we know what tools are available to us. We're going to look at the formula option first for each one, and then we'll look at the time value money keys after we've evaluated it with the formula. All right, so let's look at option 1 first. With option 1, we are given the present value. We know what it's worth today. It's $130 million. We want to know what it's going to be worth 30 years from now after it's sat and earned interest over that period. So we are using the future value version of the future value present value relationship formula. That is equation 3.1. Here, where the future value is equal to the present value times our interest rate factor, 1 plus r raised to the n. So future value is equal to present value times 1 plus r to the n, filling in the information we have for this problem. The present value is $130 million. Our interest rate, r, is 8%, which expresses a decimal as 0.08. 1 plus 0.08 is 1.08. And then n, the number of compounding periods in this problem, is 30. All right, so if we plug that in, we've got 130 million times 1.08. I need to raise that to the 30. So if I'm doing this on the BA2 plus, once I've got 1.08 on the display, I'll press the Y to the X key, which tells it to raise it to what I'm going to type in next, which is 30. And I can press the equal sign, and it'll do everything in the correct order. It'll raise 1.08 to the 30, and then multiply that value times 130 million. All right, so this 130 million, if I deposit it today and let it sit for 30 years, is going to grow to $1,308,145,396, roughly. And we've run out of space on the display, so it's not giving us the pennies, but what are a few pennies on $1 billion? All right, so the lump sum payout option is going to be worth roughly $1.3 billion 30 years from today if we leave it invested. Not bad. All right, let's look at the annuity option now. We already figured out that we are looking at an annuity due. And looking at the timeline, we're looking for the value at the end of the timeline, which is future value. So I want to go get the future value of an annuity due formula. So there's our ordinary annuity due. The future value of an annuity due is equal to, actually, the future value of an ordinary annuity. So this first chunk right here of this formula is the same thing as the future value of an ordinary annuity. And then we're going to multiply that times our interest rate factor of 1 plus R. So first, let's verify that. Let's go look at the future value of an ordinary annuity formula and see that these terms do in fact match. For an annuity due, we've got payment over R times the quantity, 1 plus R raised to the n minus 1. That's our first few terms in the annuity due formula. And we take that entire amount and multiply it times 1 plus R. Well, if we scroll up and look at the future value of an ordinary annuity, we see this exact same expression. The payment divided by R times the quantity 1 plus R to the n minus 1. Okay, now why are these formulas so similar? Well, if we look at our timeline here for an ordinary annuity, if we're calculating the future value of this thing, so we're running all the cash flows out to the end of the timeline, we can see that this last cash flow here, in this case, this last $10,000, is already at the end of the timeline. So if we were looking, in this case, the future value at the end of year 3, this $10,000 is already expressed in end of year $3, and it does not need to be compounded. We would not add any interest to this. Now, the cash flow right before that needs to earn interest for one period, needs to be compounded one period. So we would find the future value of this payment just one period later. So we'd multiply it times 1 plus R to the 1 to find the future value one period later. This first payment, in this case, needs to be compounded 2 periods from the end of year 1 to the end of year 2 to the end of year 3. Right? So it would be multiplied times 1 plus R squared, or raised to the 2, to compound interest over 2 periods. If we compare this timeline with the annuity due, here, look at the last cash flow on this timeline. This $10,000 happens 1 year before the end of the timeline. If we were finding the future value of this annuity due, this last $10,000 payment would in fact earn interest one period. So we'd multiply it times 1.R to the 1 to find the future value of it. We did not need to do that with the ordinary annuity. This one was already an end of year $3. So if we were to apply the present value of an ordinary annuity formula to an annuity due, we would have one fewer compounding periods applied to every single payment. That is, this last payment needs to be compounded one time, the second payment needs to be compounded 2 times, and the first payment would need to be compounded 3 times, 1, 2, 3, to get to the end of the timeline. That wasn't the case with the ordinary annuity. So we need to apply to every single cash flow one extra compounding period in order to get them all out to the end of the timeline, and that is exactly what this last term does. This last interest rate factor that we're multiplying on here takes the entire cash flow chain, the entire payment chain, and adds one more compounding period to it, just to recognize that each cash flow is happening one period sooner, and so each cash flow gets one more period of compounding to earn interest if we're calculating the future value. Okay, so let's actually apply this formula where the future value of an annuity due is equal to the payment divided by the interest rate times the quantity, 1 plus R raised to the n, so 1 plus R raised to the n minus 1. and then times, again, our interest rate factor to get that one extra compounding period added to it. So we're just using this future value of an annuity due formula. Okay, plugging in all the information we've got from this problem, our future value is equal to the payment, which in this case is 10 million, divided by the interest rate, which is 8%, expressed as a decimal is 0.08, times the quantity, 1 plus r, where again r is 0.08, 1 plus 0.08 is 1.08, raised to the n. Now this can be a point of confusion with an annuity due. That n is going to be 30. 30 here, this n is the total number of payments in the annuity, or the total number of compounding periods of this annuity. Now that can be confusing because the last payment on our timeline actually occurs at the tick mark underneath 29. But again, that n is the total number of payments. We started counting those at 0, and so the 29th, or the $10 million that's underneath the 29, is actually the 30th payment. So we want to make sure we account for all 30 payments. So that n is going to be 30. Subtract 1, and then multiply the whole thing again by 1 plus r, or 1 plus 0.08, which is 1.08. All right, when I'm working these problems, if you have your calculator set up, your BA2 Plus set up to follow algebraic rules of operations, you can enter it just like it's written, and it'll be okay as long as you type everything in exactly right. If you're using a scientific calculator, that's a little easier because it'll typically have a bigger display and you can see the whole string of arithmetic going in and know if you've made a mistake. But even then, I'll find myself making mistakes a lot of times partway through the expression, and I won't realize I've done it until I don't get the right answer back. So I find it's actually faster for me for these type of problems if I instead work it chunk by chunk. I'll divide it up into 3 sections and then store each value as I go. So that way, if I make a mistake, it's easier to go back and track down where the mistake is without reworking the entire problem and never really knowing where the mistake happened. Like when that happens, if I get a different answer and I don't know why, I'll work it 2 or 3 more times until I make sure I get the same answer over and over again, and it ends up taking forever. So instead, I'm going to work this just from left to right in 3 separate chunks. I'm going to start with 10 million divided by 0.08. Equals 125 million. And I'm actually going to store that on the number 1 key. So I'm going to write STO1 under that for my notes. And this one works out to a nice round value, so I'm not gaining any precision by doing this, but I just don't want to type the whole thing in again later when I'm going to multiply all 3 pieces together. So I'm just going to store that value so I can hit recall 1 instead of retyping in 125 million in just a minute. Okay, now I'm going to work the part inside the brackets. That's 1.08 raised to the 30, and the way I raise it to the 30 on the BA2 Plus is by pressing the Y to the X key, which is going to raise the value on the display to what I type in next. In this case, that's 30. And I'll press equals, and it'll go ahead and do that exponential function for me. It did 1.08 times itself 30 times to come up with 10.0627. And I want to subtract 1 from it. So minus 1 equals, so the value inside the brackets is 9.0627, and that is not a nice round number, so I certainly want to store this value. Say store that on the 2 key, and when I stored it, it's not storing this 4 decimal approximation, it's instead storing the 13 decimal version that it has worked out internally, so that when I then, in a moment, multiply this number times 125 million, I'm going to get a lot more precise answer than if I just retyped in this 4 decimal approximation. Okay, that last chunk is just times 1.08. I think we can handle that without using the memory functions. All right, so let's multiply this guy out. We've got recall 1, which is our 125 million, times recall 2, which is at 9.0627, and then times 1.08 equals. All right, so the future value of the annuity payout option is $1,223,450,000 458,680. Again, it's not showing us the pennies because we run out of room on the display, but what is a couple of pennies on over $1 billion? All right, so what does this value represent? This value represents the future value of the annuity payout option. And another way of thinking about it is our account balance that we would have if we received each payment, invested it at 8%, and just let it all sit there and earn interest for 30 years. So if we did that with the annuity option, we'd have $1.22 billion in our account, roughly. If we did that with the lump sum option, we would have $1.3 billion. So in this case, if we're considering the future value option, 1.3 billion is definitely greater than 1.22 billion. So we would want to take the lump sum payout. Because we will have more cash available 30 years from today. Now, if you've already watched the video, you've already worked through the previous example, 1.4.6, where we found the present value of this exact same annuity and lump sum option, you'll recall that we came to the same conclusion, that the lump sum payout option was more valuable to us, and we would have accepted that. In this case, we don't have to, it is not necessary to solve both of these for both present value and future value. It is not as if we look at it from a present value perspective, we come to one conclusion, but we might come to another conclusion if we look at the future value perspective. We're going to come to the same conclusion either way. We're looking at the same cash flows. They have the same relative values. All we're doing when we're looking at present value versus future value is changing the units associated with those numbers. It's still the same relative values. One is just, in present value terms, it's today's dollars that we're looking at. And then in future value terms, it's dollars 30 years from today that we're looking at. So it's just expressed in two different units, but it's the same relative values. You would not need to do this analysis twice. The only reason we're doing it from both present value and future value perspective is just to get exposure to the mechanics of both of those calculations, and also to see that you'll come to the same conclusion. That's worth knowing as well. Okay, let's look at the time value money keys solution. If we're looking at the lump sum option, I'll write out my time value money keys in the same order that they appear on the calculator. I just like to write them vertically because that's the habit I got into early on. There's no special magic to that. N is the total number of compounding periods. Same thing as the N from our formula. That's going to be 30. I over Y is our interest rate. It's that same 8%. Just when we're plugging it in for I over Y on the calculator, it knows that a percentage is coming, so we put it in percentage format instead of decimal format. So we're going to plug in 8 instead of 0.08. Present value is what happens at the beginning of our timeline, so with that 0 tick mark on our timeline. With our lump sum option, that is a cash inflow of 130 million. So on the present value key, we're going to put 130 million. Payment is if we had a reoccurring payment over and over again. We don't have that in this case. And what goes on the future value key is future value is what we're solving for in this case. So that guy's going to be a question mark. All right, so let's plug those in. I'm going to start, as always, by clearing out the time value of money keys. So I'm going to hit second and clear TVM to zero everything out. And then I'll just enter them from left to right. N is 30, so I'm going to type in 30 and then press the N key to store it. I over Y is 8, so I'll press the 8 key and then I over Y to store it on that key. Present value is 130 million, so I will type in 130 million, press the present value key to store it. Payment is 0. It should already be 0 because I cleared it out, but just to be sure, I like to go ahead and record 0 on that key. So if nothing else, I've physically punched something in onto every key and I know what is there without just having to have faith that it cleared out. All right, future value is what we're solving for. We've got 4 of the 5 entries in, so the calculator can solve for the 5th for us. We can hit compute FV to solve for future value, and we're going to get a future value, in this case, with a negative sign in front of it, which just says that the relative direction of the cash flow is in the opposite direction as the present value that we plugged in. That's 1,308,145,396, which, if we look back up at our arithmetic, when we just use the formula, is the exact value that we came up with before. Again, the calculator with the time value keys just keeps track of the relative direction of the cash flows, so that minus sign just means the cash is moving in the opposite direction as the present value. It doesn't mean that it's a negative value. In fact, if we want to, we can switch the sign on the present value. You, of course, don't have to do this. This is just to show what happens. If I record that present value is a negative and say compute future value, I'm going to get the exact same numerical value back. It's just not going to have the minus sign anymore. We'll just flip the signs on us. All right, let's look at the annuity option. And this is where things are a little bit different. I'm going to use the same 5 keys, of course, the N, I over Y, PMT, and FV. N is still the number of payments or number of compounding periods. That's 30. And what we're entering here is the second timeline, where we have these 30 payments of $10 million, and we want to find the future value. Right, I over Y is still 8%. Present value in this case is, I'm actually going to record a 0 here. And let's go right to the payment first before we discuss why, because it'll make more sense if we talk about the payment. On the payment, that's that recurring payment that happens over and over again. It's going to happen however many times. It's going to happen the same number of times that we enter for the N key. So if N is 30 and payment is 10 million, what we've told the calculator is we're going to receive 30 payments of $10 million over the next 30 periods. Of course, future value is what we're looking for, so we'll put a question mark there. All right, present value being 0. That is not saying that the present value of this annuity is 0. What we put on these cash flow keys, the PV, the PMT, and the FV, are what actual cash flows happen at that point on the timeline. Now, in time period 0, we do have a $10 million cash flow. That is there, but I still recorded 0 for present value because we set payment equal to 10 million and told it we were getting 30 of them. So we have accounted for all 30 payments of $10 million by just putting it on the payment key. If there was some other cash flow here in addition to that first $10 million, maybe they give us an extra $10 million bonus, or let's pick a different number so it won't be as confusing. Maybe they give us a $5 million bonus for accepting the annuity rather than the lump sum payment. So if we got $5 million in addition to this $10 million, then we'd want to put that on the present value key. But that's not what's happening here. We just have the 30 payments of $10 million. So we're going to leave that present value at 0. Okay, let's plug everything in. I'll hit second and clear TVM to 0 everything out. Then N is 30, so type in 30 and press N to store it. I over Y is 8, so I type in 8. Press I over Y to store it. Present value is 0, which it should be after I cleared it out, but just to be sure, I'm going to record 0 on present value. And then payment is 10 million. So 10 million, and then press payment key to store it. We've got 4 of the 5 values in, so the calculator can solve for the 5th, which we will do by hitting compute future value. Right, and we are getting 1, 3, 2, 832,111, which is a different value than we got with the algebra. So let's check everything. See if we put something in. Oh, I created a teaching moment inadvertently here. So let's hit compute future value and see what we came up with. So we're getting 1,132,000,000 and change, which is not what we came up with the formula. And that's because I did not change the mode on my calculator. It is still assuming that payments are happening at the end of the period, right? Because it's in end mode. I didn't put it in begin mode, which we'll do in just a second. So notice that this is slightly lower. This future value is slightly lower than what we came up with on the formula. And that's because, as we talked about with the formulas, there needs to be one more compounding period associated with this to get it to the right place. In fact, so what we just did actually was we had the calculator calculate this first part of the formula right here without this extra 1.08. So if I were to take this value and multiply it by 1.08 equals, we'll actually get the exact same value. So I'm just missing one compounding period on that future value. Now, you don't have to do it with time value keys and then multiply times 1.08. Instead, let's leave all of our time value money keys in there, and let's tell the calculator that we're dealing with an annuity due. So what we need to do is put our calculator in begin mode. Right? And the way we do that is with this BGN key right above the payment. That is like a toggle switch that'll flip the calculator back and forth between annuity due and ordinary annuity mode. And the way we access it is by hitting second in BGN. And it comes up in end if we're in end mode. And we want to toggle that to begin mode. And the way we toggle it is by hitting second and set above the enter key. So second set, we'll see it flip to BGN. And we see BGN in the upper right corner of the display. Now that's going to stay on the display even when we exit out of that menu, because working with an annuity due is an odd thing. Most of the annuities we run into are ordinary annuities, so this is like a big warning sign from the calculator that's telling you, hey, I am assuming payments happen at the beginning of each period. Are you sure that's what you want to do? And in this case, we do. So all those cash flows are still in the time value of money keys. I can check them with the recall function if I want. I can say recall N is still 30, recall I over Y is 8, recall present value is still 0, and recall payment is still 10 million. So now I want to have it recompute that future value, assuming that each cash flow is happening at the beginning of the period. So compute future value, and sure enough, we come up with the same value that we got with the formula. That's 1,223,458,680. All right, and again, the negative sign is just keeping track of the relative direction of the cash flows, and it's not saying the value is a negative 1.2 billion. It's just saying that cash flow is moving in the opposite direction. So once again, with the calculator, I come up with the lump sum payout option is 1.3 billion. Which is greater than the 1.22 billion of the annuity option. So we would want to take the lump sum option. All right, with the lump sum option, we deposit that 130 million, let it sit for 30 years, and we're going to have $1.38 billion in our account when we're ready to start drawing down on it. And under the annuity option, if we did the same thing, we take every cash flow and deposit it and earn 8%, we'll have only, and I'm using air quotes so you can't see, only $1.22 billion in our account, which is less than, in fact, it's almost a full 100 million less than what we would have under the lump sum option. So the lump sum option is more valuable to us, and that is a function of the interest rate that we are applying. If this interest rate goes higher, if we can expect to earn more, so instead of 8%, maybe we think we might earn 12%, then it's going to be more valuable to receive our cash flows sooner so that we can then invest them and start earning that interest rate. We want that interest working for us. So the higher the interest rate is, the more attractive the lump sum option is going to be because we're getting the cash flows sooner. The flip side of that coin is the lower the interest rate is, the more attractive it is to delay those payments because the actual sum of the annuity option is $300 million. We're getting 30 payments of $10 million, which totals $300 million. So as the interest rate decreases and we can't have interest working for us when we receive the cash flow sooner, the annuity payout option is going to become more attractive. And there is a point at which, I don't know what interest rate it is, I haven't sat down and figured it out for this example, but at some point our decision would flip when interest rates are low, and it would be more attractive to take the annuity option because those nominal cash flows are actually higher. right? So the decision we come to, the point of all that is the decision we come to completely depends on the interest rate we expect to earn on those cash flows. It's not a given that the lump sum option is always the superior option or always the option that would give us a higher present or future value. So it's something you've got to evaluate every time and try under different assumptions, because of course you don't in real life know what the interest rates are going to be. So you want to get an idea of how sensitive that decision is to the range of interest rates you might expect. Or not necessary for this problem, it gave us one interest rate and we figured it out. As always, we went through both the formula solutions and the financial calculator solutions. You do not have to do both. They're both going to get you to the same place. The idea is just to be exposed to both. We can look at the formulas and get an idea what the calculator is doing for us. And some students are more comfortable continuing to use the formulas just because you can see it laid out and you see the math making sense. A lot of students are much more comfortable using the time value money keys because it goes faster. There's fewer opportunities to type something in wrong and so on. Whatever option you want to use is perfectly fine. I just want to make sure we're exposed to both as we work through these examples.